Hello everyone, welcome back to my channel. If you support and like my work, please subscribe to my channel before starting the video. Today we have a lot to do and I will start talking about machine learning, which is a driving development across many fields in science and engineering. Roughly saying, we can say that machine learning specializes in how computers simulate or implement human learning behaviors. By acquiring new knowledge and skills, the existing knowledge structure is reorganized to improve its performance. And here is where Julia language comes in to help us, since it aims to solve the two-language problem, bringing us the best of both worlds: efficiency and simplicity for high-performance programming and data analysis. With these advantages in mind, we are able to list some of the main applications of Julia language to machine learning development and improvement. It is extensible from Internet of Things, computer vision, autonomous driving, pattern recognition, natural language processing, and graph analytics. Compared to other languages, another amazing thing about Julia's machine learning ecosystem is, while PyTorch and TensorFlow include entire separate languages and compilers, Flux.jl is just Julia-based. All of this is possible by implementing the core of machine learning algorithms in Julia that can be divided into supervised and unsupervised learning. Supervised learning learns the training samples with class labels and then predicts the classes of data outside the training samples. All the markers in supervised learning are known. Therefore, the training samples have low ambiguity. It can mainly include classification and regression algorithms. On the other hand, unsupervised learning learns the training samples without class labels to discover the structural knowledge in the training sample set. All categories in unsupervised learning are unknown, thus the training samples are highly ambiguous. Two of the main methods used in unsupervised learning are dimensionality reduction and cluster analysis. More complex algorithms such as deep learning, artificial neural networks, and extreme learning machines include both supervised and unsupervised learning. Our example today will focus on creating a neural network in Julia, using tools from Flux that can play well with others from SciML organization. SciML is an acronym from Scientific Machine Learning. SciML is not a standard machine learning. SciML is the combination of scientific computing techniques with machine learning, helping us to solve problems in biology, physics, and chemistry. Thus, this organization is not an organization for machine learning libraries. Rather, SciML is an organization dedicated to development of scientific computing tools which work seamlessly in conjunction with next-generation machine learning workflows, providing well-maintained tools which compose together as a coherent ecosystem. It has a coherent development principle, unified APIs over large collections of equation solvers, pervasive differentiability and sensitivity analysis, and features many of the highest performance and parallel implementations that one can find. Now, it is the time for a beginner example without external data, just for fun. It is based on this post on Medium, a really good one if you are a beginner on machine learning studies. At first, we will import all the dependencies we will use, beginning with Flux. In this example, we will use a neural network to predict Unix epochs from a given date time. So, we will need to import dates.jl. Just to clarify, an epoch time is the number of seconds that have passed since midnight, 1970, January 1st. We can get an epoch time from datetime in Julia by calling the datetime to Unix function. Considering that now we know how to do it, let's say our training data are between 2010 and 2020, and we are only interested in predicting values up to 2030. That is our test data. To do it, let's set the variables as first train epoch, last train epoch, and last test epoch, respectively. Now that we know what y's can vary between, we can take a couple of samples and create our own data. Not that we don't need to download anything from anywhere. We will make our own data by setting a random seed and defining the y variable. Since we are building a neural network, normalizing our inputs is kind of a must. But since our outputs are so large, on the scale of 1 billion, we'll also need to normalize our outputs. This way, we can avoid waiting for the neural network to reach the huge weights it would need. We will also set a function that transforms our predictions back to the correct scale. And we will separate our x values into year, month, day, hour, minutes, seconds as inputs. We can also use mini batches to speed up the training, and itertools partition function makes this easy. We will use a batch size of 10 and then form our x and y's values. Finally, now we will build our network and train it. To start off easy, we will just use a single layer and identity as our activation function. Since we have 6 inputs, we will set a model with a dense of 6. This model is our neural network architecture. Here, the loss function that we will use a mean squared error imported from Flux. And we will use ADAM as our optimizer to update the weights during the training. To train our network, we pass this into Flux.train together with our input and output data pairs and iterate of our data a couple of times. We will call each interaction as epoch. And then we plot our loss function for the period between 2010 and 2020. To predict the values, we will need to rescale our prediction back to epochs, building a new function. If we take a look at the difference between the inputs and the predict epochs, we will see that the range we have is between minus 30 hours and 30 hours. This shows us that our predictions were not too unsuccessful. But our predictions are not perfect, and there's a room for improvement. I suggest you to test new optimizers and build another loss functions with more data. To a depth look into Flux.jl and its use with SciML tools, I strongly recommend you to read the amazing tutorial that Chris Arrold, Nicholas Korsbol, and Chris Rakokos posted in the Julia Lang blog. Since we have finished the first part of our machine learning series, I will give you a spoiler about the next video, where we will discuss automatic differentiation and how SciML ecosystem can help us to calculate it. So, thank you for your time and attention. Please click on the like button to support my work on YouTube, and bye. See you in the next video.